On yet?
So, how
Hey, Santiago.
much? Hey, Nasari.
Is the backgrounds generated by LLM code, Mash?
Hardly. The background is just something free from Canva that I was playing around with, put into Zoom. If you want it, I'm happy to share it.
I'm good. Thank you.
Yeah, I mean, Zoom isn't exactly as exciting of a tool.
Hmm. Yeah, true. Some is kind of weird. I don't fully understand how it became so popular during the
Yeah.
pandemic. I mean, it
Yeah.
works
Hmm.
really well, but like the UI and stuff, it has been getting better. But I remember at the beginning was kind of messy.
Agreed. Does anybody even remember Skype anymore? Skype was an
Hmm.
awesome technology. Even now, the protocol that Skype uses, that was originally developed, which was in a very peer-to-peer approach, still very,
Yeah, absolutely. I'm from Estonia, and whenever it comes to the technology, everybody's mentioning around Skype. But sadly, it's
Hmm.
it's a kind of more like a legacy in the history.
yeah. Skype was developed in originally in Estonia, was if I'm not mistaken, it was Estonia or oh,
They had investors from Denmark and Sweden, I guess, and
mhm,
then two main engineers were from Estonia.
that's right. All right. Can I get
Or,
5 minutes,
yeah,
I guess, to start with positional encodings?
and
Well,
indeed,
15 minutes. Mhm.
indeed. Just put everybody on the same page. Marsh is gonna give. I put 15. If you take five, it's great. But yeah, 15 minutes to finish just wrapping up positional encoding embeddings, encodings. Yeah. And then Eddie is gonna take start with attention mechanisms. He's gonna present like the background of where they come from, and then explain simple self attention. That you see that Sebastian splits attention mechanism in four examples, like simple self attention with no trainable weight, then self attention with trainable weight. This is like the core part, and then causal, and then multi head attention. So the last two we will probably like discuss in the next session. Today we will focus on this first two. And then for us, the task at the end of the call is to pick who's gonna be next week's lecturer. So yeah, Mash.
All right.
With that said, I think the floor is yours.
Very good. Let me share my screen, share the whole screen. All right. So let's pick up where we had left off last week, which was around the core notion of building tokens and the embedding layers and so on. So we figured we walked through how you get the weight matrix for all the embeddings and so on. Now, one interesting, and I'm going to jump and use another uh, document, if you would, to help explain this point. This is yet another book that basically tries to say, we did that traditional linear structure for embeddings, but when you're training a model with lots of different documents, lots of different bits of information, and you start saying, well, just learn on this much, that's going to be inefficient because you're saying, okay, we're going to start training from position 50, where remember in this model, we wanted to, this is going to come later with attention, we wanted to understand the information before and after. Hence, there has to be a more efficient way to recognize the position of the different embeddings, which we'll get to later. So that being said, get right back to it. This is how Sebastian, and I actually have some additional points that I'm going to share. Let me expand this. So the whole idea is you want to have some kind of vector that recognizes the position of a particular embedding that you're interested in. Why is that really necessary? As you know, we want to try to build code that is going to be efficient. So here's the way to think about it. You've got a whole bunch of input codes. Let me see if I can make this a little larger. And then each of those tokens will have their own embeddings. And in the code that Sebastian uses, you also generate a vector for its position, and then you blend them together. And this works because a little bit of matrix algebra here, they're roughly the same dimensional length. Now, as you can see, this is me using Mermaid, trying to get that intuition here is when you put it all together, this becomes a lot more efficient in order for us to be able to build a model that isn't just going to start from position 0 and that's everything, that's the entire world. You're now allowing the model to be a lot more flexible in being able to take different chunks of information at different points in time. Any questions up to this point? Yeah, for some reason I can't see.
Just a basic question, Mash. What? So you can hear me?
Yeah. You are.
Yeah. So what information is contained in the position embeddings in terms of other than just the position part? I mean, what makes it an embedding worthy rather than just okay, this is at this, like, more than just an indexified information? What information is there?
That's a really good point. My understanding is, and this is where I'm not an expert, my understanding is it is the position index. I believe there's more information there, and this is the part where I struggled. And I had it try to explain to me using Claude, how did you implement it? What's going on here? So it tried to say, all right, there's this, that positioning has this sinusoidal information there too. And apparently that has some kind of value. So Naveen, that's a really good point. Why that is, it isn't just a position vector or index, that there is something more there. I couldn't figure that one out.
Yeah, I remember. Yeah, now there's something sinusoidal point there. But okay, I can look that up. Yeah.
What was the question, Naveen? I didn't catch it. Can you please repeat the question?
So the question is the position embeddings, why they are even going to be important as we go, Eddie, into attention mechanisms and being flexible. What additional information is in the position embeddings? We know the token embeddings. That's the structure, that's information, all of that, right? We talked about byte pair and so on. But the position embeddings for different chunks of information, it shouldn't just be simply a index of its position, that there has to be some kind of information, like this sinusoidal information.
So
That.
I might be able to add one or two snippets, but not much detail. So imagine that you have input data scaled between 0 and 1,
Mhm.
your embeddings,
Mhm.
and now you want to add a position to it. So the type of information in the position, is it the first word in the document? Is it the second word in the document? Is it the third word in the document? Is it the 100th word in the document? So if you use just word number, for example, token number, you end up very quickly with numbers between 1 and 100. And that has a very different scaling to the input between 0 and 1, and it makes it computationally difficult to deal with. So you want to make sure that the scaling is roughly the same between the input embedding and the position embedding. So sine and cosine, of course, are between -1 and +1. And so that allows you to have some control over it. The second thing is that you don't necessarily know in advance what the length of the sequence is. So you want to use a technique that allows you to have different length sequences. I think those are two of the minor details around it.
The different length sequences. So if you take a chunk that has a certain specific, it's an extract. So obviously it's going to be a smaller sequence length. And then you create a new positional embedding of that smaller sequence length. And when you merge them together, they're the same dimensions. Is that a fair point?
So yes, of course, they have to be the same dimensions, but numerically, if position 5 has a different meaning in a 100-word sentence to a 20-word sentence, perhaps it should have a different value in the embedding too. And I'm not sure if that's actually what happens, but you could see that could be one reason. And then if you have something that's trained on 100-word input sequences, what happens when you want to use a 200-word sequence? If you use the numbers 1 through 100 and then 100 to 200, there'd be nothing in the training that would reference the 100 to 200 range. So perhaps maybe you have to interpolate between 1 and 100, and I'm not sure how that works, but I think the techniques using sine and cosine are probably easier to get the scaling right.
Yep.
Yeah, I would like to add a few more points. I think Peter covered most of the intuitions. Actually, I sent a link in the chat, which is a link to a blog. I think it has a good visualization that might help understand the topic.
Okay, my take on that is that if we take a simple sentence, yeah, if we don't have this positional encoding, the tokens we have is just a bunch of numbers which have no meaning. If we need to add an additional layer of, let's say, a grammar representation in order for the for this tokenization to be useful. For example, in German, the verb is in a sentence is on the last position. Yeah, so this is a very important information to be somehow captured in order to be able to make a translation. So in German, if you want to say, let's say, a sentence or a phrase, I should say a phrase, you should wait until the end of the phrase because the verb is at the end of the phrase. So this is super important to capture in a way in which the model knows that it must wait until it sees a verb, because this is when the phrase ended.
Agreed, Eddie. The position information is important, but We were trying to understand why an embedding, why not just a simple index? But I think we have a starting point with ideas. And thanks, Eddie, for it.
Mash,
Well,
could you bring
I
up
can
the
I can extend a little bit because we can ask the same question for embeddings. Why we should not make simple indexes? Yeah, and I think it basically is the same question if we apply it to standard words or standard tokens, correct? And I think the answer is within an embedding, we don't, let's say, embed the word per se, but also the synonyms, the context in which that word can appear. Yeah, and because if you have a word bank, for example, yeah, the word bank can mean different things in different contexts. That's why if we embed the word bank, you need to make sure that it's a financial institution or it is just a side of the river. So embedding is a more, let's say, enriched mathematical representation of a concept. It's not just a one-to-one mapping between the between that word and some random numbers.
Yeah, I think Eddie hit that point, Naveen, that point that you asked, that positional embeddings should contain that information. It's what Eddie just described. It's that nuanced bit of information that says the token in this context means something else in this chunk or extract.
True, yeah. Thanks. Yeah, I was starting point to think, and thanks for the links shared in that. Yeah, thank you, folks. Yeah, please go ahead.
I can add another thing.
Go ahead.
So I was looking into this positional embedding, but as I understand is, in the code you shared, Mash, there is like, I think, sinuswidle or something like that, and I think that's come from the formula of the position embeddings because it has cos and sine, cosinus and the sine. So, for example, if you see the link I shared in the chat, said that the cos means the cos formula it's used for the, how can I say it? In French we call it ampere, the impair numbers. Let me just see what is exactly.
Is there a specific place
number?
Yes, the odd and the other numbers. There is odd and pair. Yeah, sorry.
Even.
And for example, the sign is for the pair numbers, and the cos is for the odd numbers. And this is this is how it's calculated, and I think it's kind of answered the question that Navier asked for how it's really contains. It contains that, and it's based on the position of the token. And yeah, I think that's it. The position and the token and the dimension of the embeddings as well. Yeah, that's what I understood from that. If it does help somehow.
Thank you, Naima.
I just want to add on to what was explained in this blog. I think the diagram that I shared, if you scroll a bit down.
Sure.
A bit more. Yeah, this one. Yeah, it's similar to the diagram that was in the other blog as well. So here the x-axis is the position of the words, and then the y-axis is like every single position, and then the x-axis is just like the different embedding numbers. So this one is of so the position embedding is of size 128, and then it encodes 50 positions. So if you see position 0 and 1 vertically, 0 and 1, the positions, on the top, you see on the Y top, that's 0th position, and 0 and 1, they look very similar, right? Now, as it progresses down, you see that the nearby positions always look similar, but then if you compare position 0 to like 10, you can see noticeable amount of difference, right? So that's what the cosine and sine are doing. The nearby positions look similar to each other visually, but then as the position increases, there is still some amount of difference that's happening. So it builds a gradient of sorts.
Yeah, that's clear. The axis being this way threw me off, but that is the point, that you want to have some representation of how close the meanings are, the informational meanings are.
Yeah, that's exactly what it does.
Mhm. Yeah. Thank you, everybody. And just moving on and using just this blog. And again, this tries to capture relative positioning. Places up the proof, and then the sinusoidal positioning. Okay. Rather than going on with overall back to the code on positional embeddings, do we all have a sufficient amount of insights on positional embedding so we can continue to the next chapter now, or would people like to get a better sense of it?
Well, this is good for me. Yeah.
For me as well, conceptual level is good.
Yeah.
Thank you.
Thanks, Nash, for doing a great job setting the tone.
Yeah. Thank you.
This bit clearly is hard for all of us. So thank you. Eddie, do you want to take it over?
Yes, thanks, Mash. I'm sharing my screen. Can you see my screen?
Yes, we do.
Let's go in presentation mode. Here we go. Okay, so the next chapter is chapter 3, where probably is presented
Maybe
the most.
just like, because here we see like your slides on the left and notes on the right. So
No. Can you see my presentation, or
We just we saw the presenter view, so you can just have just a full screen and then.
give me a sec.
You can just start, but without the presenter view.
So what do you see right now?
So we saw both the slides and the presenter view notes. So yeah,
The slides and the notes.
Yeah.
And
you
now?
can just, we see both.
Yes.
Next slide and the existing slide.
Let me see. Give me a sec. Can you tell me what you see right now? I'm sharing again my screen.
We can see your slides. It's PowerPoint coding attention mechanisms.
Okay.
And it's just a PowerPoint with your notes below it. If that's
Okay.
that's
Can you please guide me? How can I make only the slides to show?
if you click on the lower right hand, you can see something that looks like a projector, a little icon next to the. Go to the right, move to the little bit to the right. Yeah, slideshow. If you click there, now we can see the slideshow. We're perfect.
yeah, no, works perfect.
Okay.
And if you have another screen, it'll probably show your notes and such on the other screen.
Mm-hmm.
All right.
Okay. So chapter 3 is about self-attention mechanism, probably the most complex module of his architecture because of its, let's say, innovation characteristics and the complexity. As Sebastian presented in his book, there are 4 types of attention mechanisms. The idea of this simplified self-attention technique is to make somehow every word in a sentence to focus or to attend to all the other words in a sentence in a static way. So in this simple example with this cat here generated by AI, the self-attention mechanism which is implemented should have as the end result that every word from this sentence, the cat sat on the mat, every word from this sentence should be able to understand how relevant, how important are all the other words into this sentence. The second mechanism which will be addressed today is self-attention with trainable weights. And this self-attention mechanism builds on top of the simplified self-attention technique we will try to cover today. The third and the fourth mechanisms are so-called causal and multi-head attention mechanisms, which most likely will be addressed next weekend. Okay, before to jump into code or into any discussion about the self-attention mechanism, I want to take a step back to see why this mechanism was necessary in the first place. And in order to do that, I would like to cover in the next slides couple of the problems which we had in RNNs for the last 10 years maybe, for this specific problem with sequence-to-sequence translation. In Sebastian's book, these topics are not, let's say, very detailed because the focus is on transformers and the latest self-attention mechanism, but I think it's very useful to take one step back to RNNs to see why the self-attention was needed in the first place. So the problem in modeling with especially long sequences, especially for translation use case, was that the words, in order for a model to capture the or to be able to make a correct translation from English to German, for example, the model should be able to have a certain memory in order to wait until that phrase is finished in order to make the translation. As I mentioned earlier, especially for languages like German, the meaning of the sentence is most of the time expressed by the verb, and in the large phrase, the verb is the last word in the phrase, which means that in order for somebody to understand a German-speaking person, they be very patient until that person says the phrase, because the verb is the last word, and the verb expresses the action or the most important, let's say, aspect of the sentence of the phrase, and that requires for modeling memory. The solution, which was developed by the scientists and researchers, was this encoder-decoder architecture, in which the encoder is processing the sequential German words and creates and updates the hidden states at every step in order to understand what is the meaning of the sentence. And the final, this was basically the limitation of this solution, is that the final hidden state is used to feed the decoder, and the decoder starts generating the English text one step at a time. And which means that all the other information which existed in the previous hidden values was lost, because only the final state or the final hidden state goes to the decoder. So with recurrence, basically, philosophy for neural networks seems that they are not very good at remembering too much information from the past. And of course, everybody knows during deep neural networks, all these derivatives which are used during the backpropagation have these problems of becoming too small or too large, which means that the network is not able to learn anything, or they overshoot the process. The solution, I put it apparent because it was just an intermediary solution, or was LSTM. LSTM, which basically took the hidden state and used a memory cell to perform the same function, and then used a certain gates to decide which information should be remembered, which information should be forgotten, in order to keep the track of the story, or what is meant into a, let's say, in a complex sentence. And the same problem with long-range dependencies turned out to be the main issue with LSTM's architectures. And now I would like to, so again, I want to emphasize the idea is that in this simple translation problem, pass me the salt, the entire sequence, the entire input sequence basically is condensed into a single vector, which is then feeding the decoder. And as mentioned earlier, this condensation of the entire sentence into one single vector turned out to be the limitation of LSTM architectures. So, with other words, the link between the decoder is realized only through one single, let's say, entity, which is this final hidden encoder. Before to go to the solution, the first solution, which was created by Bahdanau, which is mentioned in the book, I'd like to show you a demo real quick.
Just on timeline, Bahdanau, along with Yoshua Bengio and another, the three of them had come up with this framework in 2013.
Exactly.
And then 4 years later, the Google researchers.
Exactly. Yeah. Exactly. This is a very important point, because the attention mechanism is not something new. It's a 10 years old, let's say, innovation, which came because of this problem which I mentioned with, and I want to show you, let me stop the presentation.
Science is all about us standing on the shoulders of other giants.
Yeah. Let me share the, I should have more experience with presentation, but
consider yourself lucky. Then you'd be a consultant. We're the worst kinds of people in the world.
Well, I'm a consultant, but I'm actually working as a consultant. Okay, so I need to share again my screen. Yeah, so here is a code. I hope the training is ready. Yeah, here's a code which is using encoder-decoder architecture. This is the English to German dictionary. I took it from Kaggle. Let me show you how it looks like. So this is my dictionary, which is downloaded here. So this is the dictionary I use from this guy's Kaggle. So this is the German to English to German dictionary. I don't know how many entries I have here. It's pretty big. It took me, I did the training while Mash did his presentation. It took me 20 minutes. So I'm importing here the NumPy. I load this data set. I create the I need to make this. I need to tokenize all the sentences to build two vocabularies, one for English, one for German. I make the mapping German to English, English to German. I make the first test Huayu to see how it performs. I introduce special tokens in order to make padding because the pages will have, you see how the distribution of the sentences will look like. And since I'm picking different, I have a fixed length paging, but because of the different lengths of the data points, I'm using this padding. So this is the RNN architecture. I don't want to go into the details of the code. I just want to show you the problem, which is the long dependencies in RNN translations. The training which I performed and started with a pretty big loss, 3 epochs, and yeah, it's not ideal, but maybe if I will run it several epochs, I will minimize this value. Okay, so now if I'm asking, for example, if I'm asking some random questions here, and I increase the complexity of the questions, because he is why. Whatever, some random examples. I want to make it fail. Yeah, and I don't have this word because he's a doctor. I need to have the words in the dictionary. Yeah, so this translation is not good. So the sentence, the input is not very big, but the translation is not good. Of course, as I said, the training could be optimized also on my side, but the point being is that such architectures have this problem with memory. So now coming.
Is the reason why the translation is not good because it fails in grammar? Like it's just doing a word-to-word translation in the same order as the English sentence?
I think it's since it's a complex problem. I think that there are multiple root causes, and one of them is, for example, how big is the data set? I didn't create this data set. I took it from Kaggle. I just look on to see if it's correct, but I didn't verify it in details. So I would say that a bigger data set might help than a bigger data set to capture all the German grammar variability and nuances. Yeah. So, German is a pretty complex language that has tons of rules and, declination and stuff. So you can build a huge data set to capture all these nuances, to have, let's say, a good model. Then the number of epochs, the optimization for Adam can be a little bit Adam can be also optimized somehow. I mean, there are multiple things which can be improved in my code to make the translation better. But I just want to make the point that RNNs/LSTMs have this, even though they are using an encoder-decoder architecture, they have this memory problem. This is the point. I don't know if I answered the question.
Thank you, you did.
Yeah. Okay. So now I don't know where I need to stop again the presentation. I know where I am. To present again my presentation. Okay, can I show my screen for the presentation?
Go to the presenter mode again.
Yeah.
But I guess that's fine. I don't know.
I'm sorry, I cannot.
You
say again? Can I continue or?
Yeah, you can continue, but if you want to make it to full presentation, there's a setting on the top left, display settings. You may be able to use that to, swap. Just swap. Yep, there you go.
Oh, okay, thanks. Thanks. Okay. So again, what I wanted to show is that this, let's say, philosophy, if you want, or this architecture of encoder-encoder, even for LSTM, is relying on one single hidden state, which is limited in terms of its ability to capture long time dependencies, let's say, in phrases. This was the idea. And also, as Mark said, this attention mechanism is a pretty old invention. It's not new. It's 11 years old now. Okay. Okay. So the attention mechanism, which was created by Bahdanau, was proposed by Bahdanau, basically means that instead of, let's say, getting rid of all the states from the encoder output at every stage, somehow the decoder should have the ability to read the information from the hidden states in the encoder. Because at every stage, there might be something relevant for the token which is in the decoder processing at one moment. If you have any questions, because this is an important topic, I can go maybe with more details about what this Bahdanau proposed in his paper. So, with other words, this mechanism proposed by Bahdanau is consisting of at any moment to assign a score or a weight to each input element in order for the decoder to know how much attention he must pay to a certain element of the input. Any questions? Because it's pretty important with. So
yeah, and if I understand Eddie, can I ask?
Yeah, please.
Yeah, and if I understand, if I go back to the original phrase, the cat sat on the mat. So, for example, if you had the incomplete sentence, the cat sat on the dash, attention will allow it to be able to focus that whatever the fill in the blank is, it is connected to cat there. So that's what attention allows it to, that for the word that's coming up, which words should it focus more attention on, right? Fundamentally, that's the articulation. That's my understanding. Is that correct?
But yes, is that correct? And the key is that every word is treated independently. So if we take, for example, the word sat, is a verb.
Mm-hmm.
So in regards to this word sat, all the other words in the sentence have a certain level of importance.
Yes.
If we take the word met, all the other words in the sentence relate to this word met differently. Because only cat basically is related with the word met.
True.
All the other words have lower importance with regards to the word met, but every word becomes a reference at the time. And we take the word the, which is an article, and how important is this word regarding all the other words in the sentence. The cat sat on the mat. So this word the is relevant only for the substantive, which is the cat, but it's not relevant for mat or for whatever. And we apply the same logic for every word in the sentence. So the word cat has a certain level of relevance for the article the, because this is grammatically correct, and different level of importance related to the word, related to the action it takes, like it sits on the and where it sits on the mat. So every word is treated independently at the time in regards to all the other words, and how relevant is that part, how important is that particular word or concept in relation to all the other words. And this is the context vector. So because you asked earlier, Naveen, with the embedding and stuff, yes. So the word cat can be embedded, let's say, in a vector, 1000 dimensions. Of course, in these dimensions, in these 1000 vector dimensions, we have a lot of more information about the concept or the animal cat, that the animal per se. We have also maybe some we have some other, let's say, animals which are related to cat, like tiger or something. So we have a range of meaningful information about the cat. But so this is, let's say, the static. This is the static approach of embedding. But now a cat can be part of several contexts. We can talk, in idioms. Is used a lot in idioms. He's a very fast cat. Let's say when you talk about a very good football player or basketball player, it's a very good cat. So in different contexts, the word cat means completely different things. So that's why merely the embedding of the word cat is not enough, which means that we need to provide an enriched representation of the word cat in different contexts. If you saw the movie The Last Dance, I love this movie with Michael Jordan. They use the word cat all the time. If you know it, it's a very, very nice movie. The Last Dance?
The Last Dance, I don't recollect, but now that you recommended it, I can.
It's Michael Jordan's life. Michael Jordan. It's super motivational. It's so inspirational. And they use in Chicago Bulls this word cat all the time. As a non-English speaker, I need to pay attention. So the word cat in this context of MBA, for example, means completely different things, and that's why we need another entity or another mathematical instrument to capture the meaning of the cat in other contexts. And the mathematical instrument or mathematical tool is the context vector, which embeds, or in its representation of the context vector, we have also the word cat, but also the relationships between the word cat with all the other tokens in the input sequence. Yeah. Okay.
Yeah. Yeah.
So question is, how do we compute these weights now?
Can I have an additional question to that?
Yes.
So basically, do you understand correctly? So you want to grasp some sort of approximate meaning of the context whenever you get the input. And then after that, you will start to get the more kind of additional context from, let's say, the foundational kind of embeddings that you have. So it's a kind of two ways, no? Or two steps. So first, to get the understanding in terms of the input, and then the next to get the understanding of that additionally into kind of a general kind of language space.
Exactly.
I don't know.
Yeah,
Okay.
exactly. So, you know, different words to give you another example of why embeddings have limitations, because it's about here a limitation of the embeddings per se as a mechanism. Idioms, you know, idioms means that you have a sentence or you have 2-3 words which depict something which have nothing to do with the words. Yeah, I cannot come with any example, but you know what I mean. So idioms is, you know, with small expression, or jargons. It's another example. Yeah, I mean, it's impossible to understand what the jargon can say only from embeddings. It's impossible, because if you put the embedding of word, can somebody give an example of a jargon or an idiom? Okay.
Push the envelope.
How? Sorry, once again.
Push the envelope. This
Yeah,
is
I don't know
something
what
that
it means.
you're
I don't know what it
saying.
means.
Okay.
I don't know what it means.
Yeah.
What does it mean?
It means getting, pushing, working harder. Push the envelope means just pushing the.
Okay, no.
To your point,
Yeah.
It's an idiom. Exactly to your point, it's an idiom where just pushing, making an effort even harder, et cetera, you know. So yeah, that kind of context, like you started with the word bank as in financial bank or a river bank. That context is really important. That's what you're trying to get.
Yeah, and that's why embeddings are not enough. Yeah, so not counting for the memory problem we started with. So that's why we if you remember last time we said, I mean, we need to go to the bottom of things, and the bottom of things is all these semantics, grammar rules, idioms, different meanings of the words in different contexts, different meaning of the words in different languages. Yeah, and we have to deal with a lot of, let's say, linguistic complexity, because this is the problem this large language model want to address in the first place. Yeah. So that's why these very creative guys came out with these very smart solutions like context vectors. This guy. Yeah. So that's why I mentioned here that it's not push the envelope. You cannot correct. It's impossible to correctly capture the meaning of pushing the envelope only using the embeddings of these 2 words or 3 words pushing the envelope. Yeah? You need another mathematical tool or instrument, and this tool is this context vector. Okay, so in the example, which I'll go through the examples, but I just want to go a little bit through the intuition right now, is this sentence, which is your journey starts with the first step, and Sebastian, the author, first he wrote here with embedding of the tokens, 3 dimensions, yeah, and then he computed somehow the attention weight, yeah. We'll see what it means in a second, yeah, and then he made the sum of all the inputs multiplied with the attention vectors. So basically, how should we read this picture? So alpha 21 means how important is token 1 for the token 2. So how important is the token 1 or the word expressed by the token 1 for the concept which is expressed by the token 2. Alpha 2, 3 means that how important is token 3 for the word expressed by token 2. So every word is in itself a reference at one moment of analysis. And against this reference, we assess how important are all the other words / tokens with regards a particular word. And in this way, we build a matrix. So the first step, I will again, I want just to cover the intuition here. The first step is that every word becomes a query, yeah, and we think about this query like as I described these coefficients alpha 2 1 or alpha 2 2. So how important is word 1 for the word 2? How important is word 6 for word 2? Roughly speaking. So between tokens, between different two words, when a word at one moment acts as a query, as a reference, we compute these attention scores, which basically means importance. How important is a word for my reference, for my query, for my word which I'm considering at one moment? And I can do that using similarity mechanisms like cosine similarity, for example. You know, from RAG, from retrieval augmented generation, cosine is a very common mechanism to identify the matches in k matches in a text. Dot product is another one which basically tells us how close one vector is to another. So as high is this product, dot product, it means that the closest are these two vectors, and which means that the importance of, let's say, of vector 2 is to the vector 1. Then, of course, we need to normalize this scores. It's a good practice because it's good to have all the sum equal to 1 because, well, it's easy to read in the first place. If we have multiple numbers and all of them make 1, we can easily say what is the participation of every piece of every element to the entire whole, the entire system. And last but not least is probability distribution. So probability distribution should be 1, and it's very easy to model and to train. And for this implementation, softmax is better than Sebastian has 2 implementation. Is better than the first one because all the values are positive, and we can map the attention weights with probabilities, which we know are always positive. And last step is to calculate the context vector, which, as I said, is the enriched embedding of a word in a given context, in a given sentence. This is the context vector. Is enriched and context related, meaning for every word in regards to the sentence it belongs to. Okay. So I will also like to continue. Please, if you have any questions, because I like also to continue with trainable weights, also to cover the intuition and then to go through the code. And if you agree, so if you have other.
So
yeah,
I had a question or like a clarification. So you showed a diagram which had a series of words, and each one of those words had a weight. That's correct. Had a weight associated with it, and then you constructed a vector from that. So I think that's different than what's described on the following slide, which is the more complicated version, where I believe what you've done is taken the dot product between the, so we're considering word number 2, journey, which has its embedding there. And I think you said we're going to take the dot product between journey and you, and the dot product between journey and starts, and etc. And so there's, just say, there are t dot products that we've taken. And the result of a dot product is a scalar. What do we do with that group of scalars, is that's what's listed in Z there. So if there's T words, we have T scalars that are the output Z there. Is that correct? We haven't used the weights alpha in that description.
Okay, let me, yeah, good question. Let's take the, okay, so can you see my PDF?
No.
Let's
Okay,
just
so,
see your presentation.
okay, let me share again. Which is the original, yeah, PDF. Can you see it now?
Yeah, yes.
Okay. So this is what Sebastian did here. So he, and this was my picture.
But yeah, this is the general picture. Maybe if you scroll down, I think there's a like the built-in one, which is as Peter was explaining, the alphas. Before calculating the alphas, we first calculate the scores.
Yeah. You are right. Yeah.
These W's.
For simplicity, the yeah. So I skipped the attention scores for simplicity because I didn't want to go into, let's say, too complicated. But yeah, you're right. I mean, I think this is the step you refer to, right, Peter? To these attention scores which are computed using .QProduct, or?
Okay, so this is calculating. So we're interested in the second word, journey, and calculating the importance of the other words in the sentence that has T words in it. So we calculate the dot product between the second word, journey, and each of the other T words in the sentence. So that's the omegas, omega. So we have T of those. And we do that, of course, for every word in the sentence. Where do we go from the T omegas, which are now a different length, to the embeddings that we're already using? What do we do with those?
So if I can chip in here, after those omegas, we scale them, right? That part is, we just don't normalize them by using softmax. So then we have alphas, right?
Yeah, from omega normalizing, and we get to alphas.
Then with the alphas, we use the alphas plus the initial input token, the initial token input, and calculate a weighted sum with the alphas. So we use the initial embedded input times like dot product alpha times alpha, and we have this C that is the context vector for that specific query token.
So let me paraphrase. If you slide back up a little, I think what you said was that we're calculating. So we're focused on word number 2 at the moment, journey. So we're calculating a context-aware version of that embedding, and we're calculating that by taking the alphas that we just calculated, which are the normalized dot product between journey and the other vectors, the other embeddings, the T embeddings. And so now we're going to construct a new version of the journey embedding that's context aware by summing, and correct me if I'm using the right term, summing the alpha times the embedding for each of the words. So alpha 1, word 1, alpha 2 word 2, which happens to be journey, alpha 3 word 3. So you're summing a weighted input sentence, if you want to phrase it that way.
Yes.
Trouble with
Correct.
the
Yeah, that's correct.
I
Yeah.
believe if you go to figure 3.17, that's exactly what Peter just summarized. So figure 3.17. I think you need to scroll down a little bit, Eddie. I
317.
believe.
Sorry, which?
317. It's up. Is it? No, scroll down even further.
Which page?
Page 69. Page 69.
Yes. Yeah,
Six.
thank you. That's easier. Yeah. Thanks, Naveen.
You're welcome.
Okay,
No,
so the attention weight
69. Page
69.
69. Yes.
69. Okay. Are you sure?
In the printed version, yes. No, no, but you are too far.
Yeah.
69. Now you're 47.
Here?
The picture below. Yeah. Go below the picture. So this
Yeah,
is
this is with trainable.
yes, but
We're not there.
yeah, no, I know, but the general picture is that let's look at the context vector, that phrase that summarizes. The last step is multiplying each value vector with its respective attention weight. So that was exactly what Peter was saying. We have the inputs, we construct the omegas by the dot products, and then we have the attention weights, and then we do this weighted sum.
So this is the more sophisticated version. Is there an analogy in the easier version that we just worked through for the key and the value vectors, or those?
I would
key
like
and
to
1 second, Peter. So okay. So the concepts key, values, and query, they exist only in the context of trainable weights.
Okay.
So it's an important. I think it's an important distinction to keep in mind that in the simplified self-attention mechanism, we don't have these concepts. We don't have yet these concepts: query, value, and key. Yeah. So the word query does not exist like it does in the trainable weights. But I think I got your question, which is a valid question. It's a valid question about the. I'm jumping so it was page 61.
Page 61, figure 3.10, I think is where you want to go.
No, I'm not there. So I wanted just to recap the steps for the simplified mechanism. Yeah. So in the simplified mechanism, because this is the first mechanism, this is a simple self-attention mechanism which I'm addressing. Yeah. I'm not yet to the trainable weights. This mechanism is without trainable weights. Trainable weights are, let's say, relevant when you talk about QKV logic. But so far, we don't consider, or this book does not consider these, let's say, concepts. And again, if we go through the steps, so the first step is to compute these intermediate values, which you are right, called attention scores, using .q. And we have with using dot product, sorry, we have these omega values. Then we to the second step is to normalize these attention scores to make them between 0 and 1, and the sum of all these attention scores to be 1. And we get attention weights. So from omega, we make through normalization using softmax, we get these values, attention weights. Yeah. And then the last step is to compute the context vector using a sum between every token and its corresponding attention weight. And this is the context vector in the simplified self-attention mechanism without trainable weights. Does it make sense, Peter?
Yes, it does. Just a minor question about the alpha 2, so we're considering the word journey, and so the dot product should be 1, and so I guess it just gets normalized down to a different value. Is that correct?
We'll see. Please address this question when we go through the code, because it's a very good question. And if you want, I can do it right now. But let me see if I can. Give me a sec to. Can I see the code?
Yes.
Can you see my collab?
Yes, we can see your
Okay.
collab.
Okay. So I'm executing now. This is the tensor for this sentence. This is the second query. This is the compute of the tensor for the second. Now it's the normalization. And the softmax implementation of normalization. And for the second word, the attention weight is 0.2.
So I finally have an intuition around that now. So of course, when our second word is journey, and that's the word that's there. And so we're going to modify its meaning by weighting it with the surrounding ones, but it's still the word journey.
Yeah. I think I have the answer to your question. So basically this number is computed in such a way in which it can express its relationships with all the other words in a meaningful way. So the word journey, as you can see from these attention weights, has the most, let's say, connectivity or importance with the words start. Yeah. So the numbers per se are not important. Their values, of course, they should be between 0 and 1. Their values is not important per se. What is important is how close are different numbers or different weights. Yeah. And if this closeness between these two numbers finds, or we can find this relationship in reality. In reality is the journey starts. And we all know that from this sentence that the journey starts with the first step. The most important word for the word journey is start, is to start, which means that whatever number represents the word journey, the word start should represent the highest, closest number to the word journey. This is the intuition behind this weight tensor here. It doesn't matter the value. What matters is if the relevant or important words in the sentence to this word randomly chosen journey are closely mathematically as they are closed semantically and in reality.
I just want to hop in and give another way to look at it, which is that the attention weights you see here I like to think them as mixing factors. So this is for the word journey, right? So we have, before we did attention, we had just the token embedding for the word journey. Now what we want to do is we want to construct a new embedding value for this one, which will have additional meaning from the surrounding words such that we can enrich the token embedding value of it. So now how we construct it is that we mix the embedding values from all of the other words using a mixing factor, and that's what these numbers are. So the new embedding for the word journey, it's going to have 23.7% of the word journey, and the word start is very important for the word journey. So we take 23% of the word start and put it into this. Similarly for all of that. Now, why is start also having a high weightage is that the semantic for the word start is important to be considered in when you are constructing the new embedding value for the word journey. So I think seeing them as mixing factors makes personally more sense to me. So I just want to explain that.
Yeah, but on the other hand, if we would extend the sentence, so you'll see where I want to go. If we extend the sentence, the journey starts very beautifully and very importantly with the first step. So if I extend the input sequence and I make the same, I calculate the same weights, this number will be probably 0.1. Yeah, because all the words in my sentence should sum up to 1, which means that the mathematical value here, 2379, is not important. What is important is the closeness of this number to other numbers, and if this closeness reflects into the semantical meaning of the sentence. Because as I said, if we make a huge sentence, these values will be smaller. And what will be important will be the relationship between a given number and all the other numbers, not how big a number is 23 or 45 or whatever. It's clear that these numbers are direct or inverse proportional with the length of the input sequence. As the input sequence is bigger, these numbers will be smaller. But again, the important is the relationship, mathematical relationship between different numbers, and if these mathematical relationships, I mean, how close a number is to the other number, reflects into the semantical meaning of the words they basically describe in a given context. Peter, I hope it makes sense if I correctly understood your question.
Yeah, I think that makes sense. Thank you.
Yeah. Okay, I want to continue with, since it's, so basically this is the first simple, thanks to Peter, we went to the practical implementation of the simpler self-annotation mechanism, and I would like to go to the second, let me share again my PowerPoint, the second implementation, which is more challenging, more interesting actually, I should say. Again, please tell me if you see my screen.
Yes.
Yeah, we can see.
Yeah. Where I think it is.
Display settings and switch. Let's see where I am.
Just to give a comment on how we're doing with time. We scheduled this call for 90 minutes this time, and we have 11 to be to meet that deadline. So probably we will have to do as with MASH this session. In the beginning of next session, you give like the closing topics on the closing like points on trainable weights, just to have that. Just so you know. Yeah.
Okay. So the first question is, why do we need another mechanism? Yeah. Why this previous described attention weights and context vector is not enough? This is the question I try to answer in this slide. And the answer to this question is that what we have seen is a statistical implementation of a context vector which depends on a context, yeah. But still we have a dimension we didn't address. And the dimension we didn't address in the previous simpler example was that we might have different tasks. We might have a summary task, we might have a translation tasks, we might have a whatever. For different tasks we might want to solve, and this to me was important for my overall understanding. For different tasks we want to solve, the way in which this context vector is computed should be different. Because, for example, in translation task, the mechanism, whatever mechanism is in place, should pay attention to every word, to every grammar aspect, etc. But in let's say in a summarization task, this context vector should pay attention to completely different things. Should pay attention to keywords, for example, yeah, which basically describe in a simple words a certain text. So, which means that this self-attention mechanism, yeah, should have this ability to understand this relationship we discussed, yeah, between inputs for different tasks, because different tasks require different approaches. And basically, with other words, an input, yeah, like we had in the cat set on the mat or whatever, the journey starts the first step. An input basically can play, or an input, an word in a sentence can play different roles. Yeah, what we did so far. In what we did so far, every word played three roles. The first role was, I'm looking for some similarities in the sentence for my input. Yeah. Another role was to offer something, yeah, like mat for the cat, for example. And another role for a word is to provide the content, the meaning, the meaning. So these three roles, which we saw that an input can play in this, let's say, self-attention mechanism, can be implemented through this query, key, and value. So every word can play a role of query, or of a key, or a key, or a role of a value at one moment in time. So for me, this was a big part of the learning curve for this attention mechanism, to have this insight that a word in a sentence can play different roles in different situations. Yeah. So now the goal is to somehow use or convert the input in order to allow to the model to represent somehow what this input is looking for, what an input is offering, and what an input is basically containing. Which means that if we have the original input, which was that simple sentence, yeah, now we want to expand the original capability for different tasks. So, which means that if I have different tasks, I want somehow to have some elements, which can be trained for these specific tasks. And here the weight matrices came into play. And the task is, or the overall goal is to project the input, yeah, into different vectors in order to encode what I'm looking for in a sequence. What we did in the simpler self-attention mechanism without training weights, we did it, but I didn't mention that. We never mentioned that when we analyze the word journey, basically the word journey acted as a query. Yeah. So the word journey acting as a query, it means that the word journey basically queried all the other words in the sentence. All the other words in the sentence basically acted as an entity which have something to offer in a format of a key, and then the value behind the key, which is the value, which is actually the meaning used to build the output. Another example is YouTube. YouTube is using exactly the same logic. So if you are looking for a video in YouTube, we are typing a query, and this query is verified, is checked against an existing index YouTube has for all his videos, and YouTube gives us back the list of videos, which basically is the value, which is the actual content we are looking for. But in our case, or in case of in this case, the driver was used different tasks. Different tasks in AI require different approaches, different kind of training for the entities which can, let's say, support that particular task. So that's why we had this, let's say, separation of from the input text. So the input text basically acts like three different roles, and in order to implement these three different roles, query, key, and value, we need somehow to project the original input we have, which is the input sequence, into three entities, which basically implement these three capabilities: query, key, and value. Yeah. So if we go now to the code, if are any question to the intuition.
Just one point which I wanted to clarify, because this query key value keeps coming up as part of understanding the attention part. And I love this articulation that you had, that query seeks, key offers, value contains. Thanks for that. It's really interesting in there. And if I understand that what we are saying is that a query is asking which of the surrounding words, how relevant are you to. The key will give a list, that which are the words that are relevant, and words are embeddings, and the embeddings actually contain the information and which is passed on to the query. Is there a way to understand
exactly
that?
Yeah, exactly. Yeah.
Okay.
So every word is a query. So every word plays all the roles. Although every word plays all the roles at different moments.
Yeah.
In the example, in the first situation with self-attention, the word journey played only the role of the query, and all the others played the roles of keys plus values.
Yeah.
But every word will play all the roles at a given moment.
True. And just to put on that, what you're saying is almost like a matrix that I can visualize, where each embedding has, let's say, a column of, what is its relevance to all the other embeddings, that information.
Exactly.
And plus, it has that the value information that it contains on its own on there. And then it's like a database. I think there was one of the comments in the Discord. The way to visualize it is like a database there. So whenever a word, its turn comes up, it looks at who are all the relevant words for me. Please, I want a list of all the relevant words for me, like a stack ranking or like that.
Yeah.
And then based on the words which are most relevant, there's some information in that embedding which is passed on there. And I'm just adding to what you're saying. Yeah. Thanks for this. This is helpful there.
Can you see my collab?
Yes.
Okay. So now, if we go to okay, so let me finish the first part because I didn't finish it. So it was the discussion with softmax, and we reached here this point where we computed the attention weights. Then the third step is to compute this context vector for the word query. Yeah, the word query acts now as a query. We know now, but we didn't in the initial presentation of this section. And we get the context vector for the word query. So basically, this is the enriched embedding for the word query in the context of this sentence. The journey starts with the first step. If we change the sentence, it will have a different context vector. And now this guy Sebastian computes attention for all the inputs, because, as I said, all the inputs will play the role of the query at one moment. In this case, it's parallelism used, and it's somehow hard to have an intuition, but we can give it, let's say, a kind of sequentially, let's say, approach in order to understand it. But this calculation is done in the same time. Yeah. So all the inputs tokens act as a query and also act as a key and as a value entities. Yeah. And we calculate this value. So this is the and then we normalize it to get value 1 to understand the because, as you see, from if this stuff is not normalized, it's pretty hard to understand what is the relevance of the word starts to the word journey. But if we normalize it, which means that all the values are between 0 and 1, like similar with the probability distribution, we see how close is the word start from the word journey. Yeah. And then we see what is the next word which is relevant to the word journey. And as we can say from reality, step is the next, which if we see, this is the third value, 0.15. So the biggest one is 0.23, which is journey. Then the next one is starts, 0.23. And the third one is step, 0.15, which makes sense. Then here we see that all the sum is 1. And we apply for all the inputs and the compute the tensor basis. And now with trainable weights, we compute the same context vector for the second token. This time we use trainable weights. And then we initialize some weight matrices. We initialize them to, I don't know what is the initial value, but we initialize them. And then we compute these query key and value vectors. Basically, we multiply our initial vector with every matrix, and we get a query vector, a key vector, and a value vector. So every time when we multiply our known input, which is the context vector, what we call the context vector, with this matrix query, we get a query vector. Then we compute, so basically now, instead of having only one vector, as we did in the first case, we have 3 vectors. Each vector has a role now. Yeah, has a clear and unique role, and this uniqueness of the role is given by the matrix. So we need also to compute the attention scores using the same dot product approach. And now we need to explicitly mention the query vector. So the new query vector is performing a dot product operation with each key vector. So basically, again, every the initial vector was somehow transformed into 3 different vectors which are called key value and query vector, and they have their roles to act as a query, as an index, or as a value. So we have 6 inputs, 6 tokens, we have 6 attention scores, and then we compute the attention scores, which doing a normalization. In this case, is use a different type of approach, is using a different approach. D is the square of D of dimension of the, and then last step is to create a context vector for the input vector using this approach step by step. I think the most important things here, as I said, is the intuition for the fact that every context vector performs 3 different roles, and in the original simpler implementation, these roles were not clearly differentiated. We had the context vector, exactly the same context vector used for all the roles, and which led to a scalability issue and computational complexity. So the solution was, if a vector has 3 roles, then the solution was to say, okay, let's make each role different and independent on the other. Of course, we use the original context vector as let's say as a source, but then we will use different matrices to create vectors for these 3 different roles. Does it make sense?
Yes. So you're progressive. Yeah. Go ahead.
No, I was just reaffirming. Mash, please go ahead.
Doing the same thing, it just progressively builds up.
Indeed. I think this way of Sebastian, starting with the simple example. Well, first starting from the RNN, and the problem was quite good because I always saw the explanation of these Q, key, and W vectors and matrices, like starting from there, like from what is the Q and the dot products, and it's like a bit weird because you lose like the motivation of why. But this way of the progressive examples and building up is really nice. I feel like something different clicked while reading this book, and of course while listening to Eddie today.
Yeah, and I was curious, Eddie, this intuition of query seeks, key offers, and value contains. Is this in the book, or is this part of the intuition that you had?
I did some research. And because it was a tough topic to me, and I wanted to go as deep as I could to find, let's say, to understand it, and I did research. It's something which I'm an IT guy, let's say, and it's something which this kind of problem exists also in IT, but of course in different situations, different context. And the idea that something, this was the key intuition for me, the idea that something can play different roles in the same time is not scalable. And then you want to find a mechanism to clearly create let's say to clearly define first the functions, and then to create an implementation for this function in a, let's say, in a different way, or in a different way, in order to address a functionality at the time. If you have if you collapse three functionalities in one object, it's hard to be scaled because all the functionalities collapsed in one single entity. Like in our first example, yeah, we have the context vector, but basically this context vector basically, or they know the context vector was the input vector. Within the input vector, we collapsed all three functionalities. Yeah, and we did compute this stuff, but in order to scale a solution, we need to make distinct entities for every functionality. So if query is a distinct functionality from value, yeah, which it is, yeah, then in order to, it makes a lot of sense to create a dedicated entity for query and a dedicated entity for value, using, of course, the same source, which was the input sequence. And we take the input sequence, which acts in the same time as a query and as a value generator, let's say, yeah. But is described, both functionalities are described by the same vector or the same entity. So if we have these collapsed three functionalities in one single entity, then the solution for, if we want to scale, is to create or to derive from this seed, if you want, entities which perform in a clear and distinctive way these functionalities. That's why we have these three different vectors. We need this query vector, this value vector, and this key vector. And how can we get to these vectors in a way in which we can have multiple tasks? Because this was another key intuition for me. Different tasks. We have summarization, we have translation, different tasks. Okay, so we need something between this original input vector and between these three new query key value vectors. We need something which should be flexible enough to address a certain use case. And this is the matrix, a weight matrix for translation, another weight matrix for summarization. Definitely the values will be different in these two matrices because the way in which the query will behave will be different in translation and in summarization. Yeah, that's why again, for me it was I struggle a lot with these concepts. I really like to struggle with tough concepts, but it's rewarding to when at least you touch a little bit and get a little bit of what the people basically wanted to develop here. Very smart guys which created these derivatives of a concept. In other words, is to have a derivative of the original vector into three different vectors, and between them you put some matrices which can be trained. It's very cool. The idea is very cool.
Great.
Thanks a lot, Eddie, for this presentation. It was very helpful. Thank you for taking that time. I don't know if someone has any last questions. Maybe we are 13 minutes past the 90 minutes limit. So yeah, please do the last questions. If not, we just continue next week. The only important thing that we remain to do is pick who would like to take on the next two attention mechanisms, which are causal and multi-hit attention. Are there any volunteers?
I would recommend Eddie stay on if possible, given that there's a certain thought process that he has started. Unless Eddie is unwilling.
Yeah, it's okay. I can do it. Yeah, I can do it. I mean, to me, this attention mechanism, it really fascinated me from the beginning. And I don't know why, but this attention mechanism fascinated me, and I really wanted to understand it as much as I could. So I really like to make this research, to go to the bottom as much as I can. And as I said, for me, the bottom which I was able to reach was the idea that in one entity collapsed several functionalities. Yeah, this was for me the deepest level I could reach out of. That, and then once I got it, everything went smoothly. But I will take, because multi-attention basically refers to different nuances of the problem, and for every nuance, let's say grammatical, semantical, you need a head, you need an entity. So I think I can do it. I can do it.
So maybe next week, and let us know if any of us can help and jump in. It'd be great. Should we, however way you want to do it, whether you want to do it with your slides or if we should go by code and kind of figure out when we're running the code why it's being framed, why the framework is set up that way, and so on. And there were a lot of other additional references that was also shared on the Zoom chat. So if you want, please, a recommendation to everybody, go into the meeting chat, and the top right, there are 3 dots, save the chat. Just click save chat. It saves it locally to your machine, so you can come back to it as well later. Because chat had some really good points.
And
All right. And Eddie, please let us know how we can all help you, and if we need to prepare for anything specific going into next week.
While I did this presentation, I realized that also because of the time, that I didn't went deep enough in the code. Maybe if I don't know, somebody can accompany me to complement my presentation with, let's say, a deeper. I'm not native in coding, so I understand how it works, but I'm not native. So, and if I reach a certain level of understanding, for me, it's enough. And I'm not sure if this is enough or it's good enough for all of you guys. So that's why if somebody can complement or help with, let's say, this code presentation, if you want.
Anybody want to step up? If not, I'm happy to help, Eddie.
Okay, cool.
And by the way, you and I work for the same company originally.
AT&T?
You were Kyndryl. I was IBM.
You're IBM.
Yeah.
Okay.
Well, was IBM. I quit a couple of months ago.
Okay. That would ask. Okay, maybe we can
yeah, let's meet.
So exchange some ideas. Yeah.
Exactly.
Drop me please your email.
Will do. Well, I connected with you on LinkedIn.
Okay, better. It's better. Yeah. Yeah.
I can pitch in if needed. Yeah, I can do that. But is this the code that you shared, Eddie? Is that part of the book, or is it on the GitHub code?
No, the RNN no, but I can share it. The RNN no.
The attention, the trainable and non-trainable, because I couldn't find it on the GitHub side of.
No, it's not. No, it's not.
This is your own. You created the complete code.
I make a compilation. I made the compilation. I can share it. I can share it.
Yeah, and that would be great.
Yeah, sure.
Yeah.
So put it in resources.
Sorry?
No, sorry. I said that you can put it in the resource channel.
Yeah. So I wanted to see, to be honest, if this link between encoder and decoder in RNN, the link between these two blocks is made through the final hidden state. And everybody says that because of this philosophy approach, the RNNs don't have memory, which makes a lot of sense. But I want to test it, and that's why I want to make this dictionary German-English also useful for me. But as you noticed, it's not very performant for reasons we discussed. But the point was to see that RNN are bad in keeping or having good memory. Yeah, I'll share it, sure. It's interesting how passion. I had another insight today that passion can make or can create so many things, like having a bunch of people on Sunday evenings instead of going out or drinking beer, and yeah, it's cool.
Well, that's what we're going to get in this group. Everyone here is committed and more eager to learn than to go out drinking.
Yeah.
No offense to anybody who loves drinking, but pass. Those things aren't good for you.
Yeah.
The younger generation don't drink anymore.
All right.
Okay.
That's great. Great to see you all also again today. And yeah, see you next week. Thanks, Eddie, again for volunteering again for next week. And thanks, Mark, too.
Thank you, folks.
See you.
Thanks, guys.
Thanks, everybody.
Bye.
Eddie.